Hi, everybody. This is Bill Bittner from IBM. Our next session is Discover the Variety of Container Technologies on IBM Z and LinuxONE. It's my privilege to introduce Wilhelm Mild, known as Willie to most of us, longtime friend and colleague. So, Willie, over to you.
Thanks a lot, Bill. And welcome, everybody, to this virtual session. And I hope next time we see each other face to face. And let's talk about the variety of container technologies on IBM Z and LinuxONE. So therefore, we will cover the container technologies or containers that can run on those platforms in different environments. And that's why I want to start with the container technologies and the ecosystem, and as the second bullet, basically to talk about how do you maintain, how do you orchestrate those containers, because having applications and having environments with containers, we're typically talking about dozens, hundreds, even thousands of containers. So therefore, orchestration is becoming very important. Now, before we're getting into details, I have an overview over the IBM Z environment. And as you know, LinuxONE is basically an IBM Z with one restriction that you can run Linux only on it. So basically you have IFLs only with a small exception, the GDPS appliance that can run on it. But other than that, you have IFLs only. That's a LinuxONE environment. On an IBM Z environment, we can run ZVSE, ZOS, ZTPF side by side with Linux environments. And I will show you here what kind of environments you can run. So basically, if you're starting from the physics of the machine, we have the CPUs or GPUs, general purpose units, or IFLs processors or ZIP processors, depending on what kind of workload you want to configure on which. But the base capacity is basically the CPU or GPU for ZOS, and IFL's integrated facility for Linux for the Linux environments. Now, even though you don't see it here on this chart, but you can even mix and match in a ZVM environment, IFLs and CPUs in the same ZVM. So basically, you are able to mix in one virtualized or with a ZVM hypervisor, you can mix ZOS or VSE with Linux in the same hypervisor, just that you know. Now, here on the chart, you see different LPARs. And if you're starting with the LPAR 1, you see ZOS on that LPAR, and you see zCX as a box inside. That's basically the ZOS container extension. And we will see what that is. I will go into more detail in it. But that's a container environment that you have inside ZOS these days. In LPAR 2, you have a secure service container. Now, this name is a little bit misleading, or you know, it's not really accurate, because a secure service container is a special LPAR. It is not an application container that we know from Docker or from containers. It's a special LPAR. And in that LPAR, we can run different workloads. Then we can have a ZVM LPAR as shown in LPAR 5, or we can have a KVM LPAR and side by side with the ZVM LPAR, so LPAR 3 and LPAR 4 shown here. And then on top of them, we have the Linux guest systems virtualized by ZVM or virtualized by KVM. What you see on this page is basically you can run everything at the same time as you see it on this chart. What I do not have here is ZVSE and the TPF, but you know, ZOS on the left side can run side by side with those others as well. And we have many customers running ZOS and ZVSE on the same box, similar ZOS and TPF on the same box. So therefore, there are different traditional environments. We're looking more onto the Linux part in this session, with one exception, to see how containers are running in ZOS. So when you're running your application now, you can run them in your Linux guest systems, as you see here. But when we're talking about containers, containers came along basically to virtualize or to have a kind of isolation for applications in a certain manner. So you can run those containers, hundreds and thousands of containers, in the Linux guests. So therefore, it is not like virtualizing an entire environment. It is an application or a microservice that is running in a container. Therefore, we can run those containers, and we can run many containers in one Linux guest, and we can run many containers in many Linux guests. Therefore, it is the entity of an application or microservice that runs in this container, and we can have them scaling or running in those Linux guests. Guess what? We can run those containers as well in the secure service container. And especially the HyperProtect virtual server that is on an on-prem service, and I'm talking a little bit about it, is where you can define in a protected environment your virtual servers, and in those virtual servers run containers. So therefore, that's a protection for an entire workload. And I had a question, there was a question in the previous session about secure execution, has nothing to do with the secure service container. Okay, in that context. And then we can run containers in a Z container extension, a ZOS container extension, as we will see. So the same containers, and you see they have the same color, they can be smaller, bigger, depending on the application, but developing one's Linux on Z container or an application in a container, you can run that in all these environments that are shown on this page. And now I'm coming to one point where when you think of running those containers, how do you manage those containers? How do you manage environments that are running those containers? And that's where a big change happened last year when IBM acquired Red Hat with their technology called OpenShift. So therefore, in the middle, the place in the middle was left empty because that's the area and that's how you can establish a Red Hat OpenShift environment on Z or on LinuxONE. It is virtualized with ZVM. So Red Hat OpenShift today is supported on IBM Z and LinuxONE as a virtualized ZVM environment. Okay, so you need ZVM for it, and you run that Red Hat OpenShift environment on top or virtualized by ZVM, where you have your master control planes or your master nodes, that these master nodes control the worker nodes where your specific work is or your specific applications is running. What is specific to OpenShift is that the Linux that it uses is Core OS. So it's not Red Hat Enterprise Linux, RHEL, or SUSE or something else. It is Core OS. So Red Hat OpenShift only runs with Core OS. And what you see here is basically the master and worker nodes in one ZVM. Of course, you can have worker nodes running in a different ZVM that you can manage from the master nodes as well. So therefore, here is basically on one chart where you can run container workloads. And now we will go a little bit to see what and how these containers work and what we call container in that context. Okay, any questions so far to this chart? Because I think that's one of the central charts that I'm coming back mentally when we're going through the presentation. Okay.
No questions in the chat, Willie.
Okay, so a container or containers in Linux, that's a technology that's not new. The Linux container org is the umbrella of the Linux containers, and basically it is a technology that came along with the goal to isolate applications in a single Linux instance or in a single Linux guest, if you want, in one Linux environment. Each container has its own address space, but has a different one, but is using the same kernel. It serves a single tasks and is a self-contained set of files. And therefore, if we compare it a little bit with what we have in the traditional world, we're calling it address space in ZOS, and we're calling it partition in VSE. So what the partition is in VSE, because you can run the same or the same subset. For example, your MQ, you can run your MQ in 3 different address spaces. Similar, you could run MQ in 3 different containers on Linux side by side without impacting each other. Everyone has its own resources that you can give it, and therefore it's an isolation on an application level, running on the same kernel, similar than they run on the same supervisor in the traditional world.
So
How?
Will, we had a question in the chat.
Yeah.
Are SSC and OpenShift on ZVM, are they supported by systems automation for ZOS and or GDPS?
Wow, there are 3-4 questions in one sentence. First of all, OpenShift today is not running in a secure service container, and it is not supporting environments in a secure service container. OpenShift today runs in a ZVM environment in one or multiple traditional ZLPARs. That was number one. Then number two was something with, can you repeat that? There was something with GDPS or something that.
Well, right. So part of number one was are either secure service containers or OpenShift and ZVM, are they supported by systems automation on ZOS?
The answer is no.
Okay.
Right now, system automation on ZOS has no connection to an OpenShift environment. That's today. And when we're talking today, it might be changed today, tomorrow, or the day after tomorrow. So, but that's today. The answer is no.
Okay. And then the other question was about support from a GDPS configuration or environment in these new environments. So SSC and OpenShift.
Okay. So as you know, GDPS has an extension called Extended Disaster Recovery, XDR, which is able to extend its functionality, so the GDPS functionality, into a Linux environment if it runs in ZVM. So a Linux environment under the control of ZVM hypervisor can be controlled by GDPS. In case of OpenShift, it is a special environment which today is not connected to GDPS yet. Okay? But again, that's today. And as you will see, OpenShift is a journey, and the journey started this year in February. So therefore, you know that's a young child, which already is a teenager. Let me say that way, because we will see. You know, it's a lot of things are possible already, but not everything.
So there's also
that keeps us very busy. That keeps us very busy in this area. Yeah.
Right.
Go ahead.
There's also a request, maybe you'll get to this later on, but talking about ZOS MF and ZOS broker being managed from OpenShift.
And that's correct. I have a chart about that. We'll
Okay.
talk later. Yes. Okay. Very good to be mentioned here. Okay. So let's go on. I talked about the technology, the container technology. Now, the isolation of these applications or these containers are done through control groups, C groups, and namespaces, or namespace and C groups, which are technologies in Linux, and therefore bringing those capabilities together makes it possible to isolate applications and allocate those applications, CPU, memory, and disk I/O, for example, from a C group perspective, and namespaces will isolate based on, you know, whatever process ID, host name, or network access, file system, user ID, and so on. So these are very important, namespaces and control groups, to have those containers running side by side, for example, with the same application, but it doesn't have to be the same application, but a container itself is isolated. So therefore, when we're looking at virtual servers versus containers, it is basically the simplicity, or a technology with a container that comes along, that you have an application level isolation versus an entire guest or an entire operating system environment isolation with a virtualization. So when we're looking at a hypervisor and the guests that are isolated through virtualization, The hypervisor can virtualize all the resources and can then, isolate those guest systems, and ZVM is certified for that as well. With containers, we're talking about an application approach, and the containers are a layered approach, as you see them here in the picture on the left side. They use the same kernel. In a virtualization, we would have the same hypervisor, but not the same kernel. You would have every single application with another operating, or with a full operating system. The container itself needs a base image. Typically, the base image is provided by the distribution partners. And then on top of that base image, you can build or install the applications or the pieces, the codes, your application, your developed application, and then close that build and have a container image. And the container image is a read-only image. It's like a golden image that you build in your cloud environment if you want. So container is a read-only image, and you can instantiate that in your dev, test, QA, whatever you want, because it is then stored in a central place where you can get it from. You can pull it from there, from the registry, and instantiate it. Important is that the containers contain the application and the Linux libraries which these applications need. So that makes them portable, extremely portable, because think of a Java application that is written for Java 1.5, and at some point in time, you're getting Java 1.8, and you don't know if they're compatible. If you have containers, the libraries are in that container, so you are not dependent on the libraries outside of your Java environment. Okay, so with that said, containers, virtual servers, containers are lightweight, very fast, startable, controllable, and therefore it is easy to scale with them. Now, containers and Docker. Well, containers were not popular before Docker came along and built a container management tool set. So Docker invented a tool set for an ease of use of the container technology. And because they teamed together with the bigger company like Google and then with Parallels and Canonical and Red Hat, they built those tool sets, or the tool set, to very quickly build and ship complex applications and not worry about where they run, how they run, just start them up. So basically containerized applications. And therefore it was an open, portable, lightweight runtime and packaging tool set that they built it. Now, when Docker started doing that, you can imagine that other companies looked at that and I like that, but I don't like this other. So there are multiple companies that build tools for developing and running such containers, or using the container technology underneath in Linux and building containers out of that technology. And with that said, when you have those containers, or when you build those containers, it's not just a tool set, it's how do I protect them as well. And the secure service container is one of these environments. As I mentioned, it is a special LPAR. That's very important. And this special LPAR means it is a closed environment. The LPAR, if you define the LPAR, can be a type SSC, and the type SSC means you cannot install on the LPAR something unless you have a protected file with a key, a crypto key, and then you use the secure installer to install that image in the LPAR and build your secure service container. And based on the secure service container technology, IBM has several different offerings that we build for that. Important to understand is that the secure service container has as a base an operating system and the management and backend with an application interface. So basically, you do not see the operating system management backend or the application interface as code. That's like your BIOS in your laptop. You have your BIOS there, but you cannot get to that code. You have specialized interfaces and processes to update it and to work with it. Similar here, you have a management user interface and the REST API where you can deploy the workload in that container environment that is available in a secure service container. All of those environments that are available today are based on this concept. So what we have today are environments or services based on the secure service container, which are in the cloud and on-premise. So you can have the IBM Cloud Hyper Protect crypto services to manage your your encryption and key management in the cloud. You can have your IBM blockchain platform, blockchain running in the cloud or on-premise. You can have your IBM Cloud Hyper Protect database as a service. And the most flexible one is the IBM Hyper Protect virtual server service or solution, where you can build virtual servers and run your container workloads in those virtual servers in a secure service container. And that can be on-premise, in your data center, or in the cloud. And by the way, for those which have ZOS and have a DB2 Analytics Accelerator, IDAA, the virtual IDA or the new IDA is running in a secure service container on Z, having underneath the Linux environment that you saw in the chart, in the previous chart. So therefore, that's a technology that we have and that we will go on with other services. And the differentiation here is, or the specifics is here, that you isolate entire workloads in that LPAR. Where with secure execution that Stefan was talking about in the previous presentation, is taking care about the execution, that during execution, you cannot have other components that interfere with the execution of that application. Here, with the secure service container, we protect entire environments, okay? Now, when we're looking at the environments that we have today based on our ZOS and Linux, on the left side, you see ZOS running native in an LPAR, or ZOS can also run under a ZVM, so in a hypervisor. And then you can have side-by-side Linux, and the applications today are processes. Normal Linux applications run as processes side by side, but they do not have that high isolation as they would have it in a container. Therefore, a container is basically building or isolating those applications, including the binaries and libraries that that application needs, and that's basically building the container. And now if you compare the Linux guest one and the container running twice application one, you know, if we compare that with the ZOS, it's basically there are two address spaces running the same applications side by side. So from an isolation perspective, it's similar, okay? Not the same, similar. Now here you see that you have a Docker engine. We will see that you do not necessarily need a Docker engine. That's what is mentioned in Linux Guest 2. That's a container engine. And we have over a dozen different container engines these days. And we will see that the focus is changing when we're talking even about OpenShift, where Docker becomes obsolete. So therefore, a container engine is running in the Linux guest, and then the containers are running side by side, isolated in that Linux. Now, what happened in ZOS 2.4 is that this Linux guest 1 and container and or Docker engine, this environment was implemented inside ZOS, and that's the ZOS container extension. So the ZOS container extension is a Linux container environment that runs inside ZOS, and it runs in the context of ZOS. So basically, as a ZOS system programmer, you do not see that it's a Linux there. It is just a container environment that it looks to you like another address space. Okay? So, as mentioned, it came with ZOS 2.4, ZOS container extension, and it executes Linux on Z Docker container in ZOS. So basically, containers that you build and can build with Docker in that ZOS. So you do, if you enable the ZOS container extension, you do not need another environment to create and run those containers. You can build them in zCX, you can run them there. Okay, and therefore, on the other hand, if you have a LinuxONE environment, you can build the containers in the LinuxONE environment and run them in zCX and LinuxONE. It's the same environment that you can use. Okay. Therefore, now let's see how that looks a little bit more in detail. Basically, the ZOS address spaces, the regular address spaces on the left side, are enhanced with a special address space, which is the zCX address space. And that you see here a little bit fuzzy presented, a Linux kernel and a Docker engine that you don't see. It is a masked environment, so basically it's hidden. And everything with that, or you can work with that environment through the command line interface, to the Docker command line interface. So therefore you can build or you can deploy those containers, and therefore you can enhance inside ZOS. You can enhance the functionality and you can enhance your applications with open source, with special container workloads, or with developed applications by the Linux teams, and deploy them and run them co-located or inside ZOS, accessing ZOS resources. Okay, so therefore every LinuxONE container can run in a such container extension address space. The special network that is used in this context is called same host. You know, in Linux we call it localhost, or in Windows. In ZOS it's called same host. It's a secure virtual network between the address spaces, the traditional address spaces, and the ZOS container extension address spaces. Okay. When we're looking at the advantage of this, is basically the whole zCX address space area, or the address spaces, you can have multiples, are managed from a ZOS context. So you have WLM, so workload management policies, controls. You can manage the CPU, so CPU management can be done. The priorities can be done. You get SMF records that you can measure that. So therefore, it is really managed as it would be a normal ZOS address space, with advantage, or with a speciality that it runs Linux containers. What you're not able to do is to look at each container, because in context of a ZOS, you will see the address space, and you look and you measure it from that perspective. When you're looking at, you know, what the capabilities are, you can have multiple address spaces, zCX address spaces, for isolation of containers, for high availability, these kind of things, for capping of resources on a per address space level, for storage assignment, for sharing resources, these kind of things. So therefore, the capabilities are there to have multiples of those. These zCX address spaces run on ZIPs, because why? As I mentioned, ZOS, it's ZOS minded. So ZOS doesn't know anything about IFLs, right? ZOS knows about ZIPs, which is a similar construct of a CPU, a special one. So therefore, your container extensions run on ZIP, 100% on ZIP, with the exception that the WLM is looking from time to time at these address spaces, and that's where you know, a couple cycles are used for that address space, but the address space itself runs on ZIPs.
So Willie, we had a question here in the chat for you.
Yeah.
So is same host the same as IUT SAMEH, the inner IP stack connectivity?
It is, let me go back. The same host is using, no, I forgot the virtual IP, VIPA. So same host is using virtual IP addresses, VIPA addresses in ZOS. So you configure the same host connectivity through the Viper method or tool set.
Okay, thank you.
And it's using cross memory or basically shared memory in that case. Okay, that's it.
Yes, that's it for now.
Okay. So as last for zCX, you know, why you would think of using zCX or containers inside ZOS? Well, here you see the integration with disaster recovery, storage resiliency, because the ZOS container extension is using as storage vSOM for allocating the storage on the disks that are attached. So therefore, you can use all the ZOS facilities that you have available to, you know, for your storage resiliency, for your disaster recovery, outage coordination, and so on. And you see here that the networking is supported or is using bypass, dynamic bypass, allowing the non-disruptive changes, failover, dynamic movement of workload, and all the capabilities that you have in ZOS as well. And the other you know, advantage is with WLM that you have service class goals, and therefore you can do capacity provisioning, SMF support for accounting and chargeback. So that's that isolation. Okay. So therefore, I think that's an environment for those which do not have Linux on Z today and are considering enhancing the ZOS capability and possibility for applications. zCX is the way to go. If you start and see that it is a big advantage, and we see customers doing that, and then they grow and grow, then it would make sense to think of going externally and then build a Linux on Z environment where you can grow even more on IFLs and then be co-located with ZOS. Okay, now why consider containers on Z as a good you know, a good idea? Is because the highest scalability on one footprint. We'll see numbers here. We're talking about millions of containers we can run on a single Z. The most secureable platform that containers can provide. Encryption performance with crypto accelerators and CPACF, as we heard yesterday, and new Linux software components and solutions in ZOS that can be made available. No software level dependencies between the container and the host. As I mentioned, the libraries are part of that container. Reuse of the same components in different scenarios like test, QA, prod. You don't have to think of, you know, is my library version 5 the same version 5.1.7.3 in QA than it is on test? Well, the library that the application needs is in the container, so that therefore you don't have that dependency. Microservice implementation flexibility is very high with those containers, and then portability and multi-platform deployment. And then the high density through the lightweight containers is given, and the reliability of Z, you know, gives the capability to run that density of the containers. And then last but not least, the bridge between development and operations, the DevOps, with the consistent tooling of the containers.
So Willie, we had another question here for you.
Yes. Yeah.
So what happens if zCX address space starts getting hot, that is CPU IO, et cetera? How do we find out what process is a problem? There's a comment about different stats being available.
So first of all, you know, to not impact the other address spaces, it is because of the isolation of the address space. If you want to find out who is the cause of it, you have to use the container methods or monitoring tools that are working on a container level, on a Linux base level, rather than on a ZOS level. Okay.
Okay, thank you.
Okay, so as I mentioned, in ZVM, we did a test, and in ZVM and the LinuxONE 3, so that's the Z15, 2.4 million Docker containers were running in a single LinuxONE system. So this is a high number, and, you know, virtualized, we could run that and scale that up. when we're running with KVM as virtualization, we compared how many we can run compared with an x86, 6.6 per unit more containers on a Linux One versus an x86. So it makes a lot of sense to do that. And as I mentioned, the portability is another point where we see that customers are thinking of, now I developed that application for x86. Is it possible to run it on Z or run that container on Z? And the answer is yes and no. It is possible to build that container for Z as well, but the Intel container itself has Intel code in it, and we can still not run Intel code, although it's packaged in a container. So therefore, what you have to know is that a Docker container is built based on a Docker file. The Docker file contains the instructions how to build that container. And the same Docker file now can be built, and the same command can be used to do it on x86, do a Docker build and Docker push. Same on Z, Docker build and Docker push. And then you build with a manifest tool, a so-called manifest, in terms of you have one name, and in that, under the umbrella of that name, you have two different images, one container image. And remember, the container image is a read-only file, one container image for x86 and one for Z. So therefore, if I'm instantiating one of these images, the manifest tool and the registries are able to understand you're pulling that image from a Z environment. So you will get the Z image, and if you're pulling it from an x86, you will get that image. So therefore, that's the multi-architecture container images managed by the manifest tool and how you can build them. Okay. Now, when we're looking at the container ecosystem, there is a lot, and I mentioned before that there are a lot of, first of all, container images which are multi-architecture support. So basically, they are built for x86 and for Z, and then I'm showing you at the end how you find them individually. And then there are multiple container runtimes that are available and different container tools. So it's not just Docker. Docker is one of the container runtimes and tool sets, but there are more than that. So therefore, in 2015, there was built the Open Container Initiative with an objective to have two standards or two standard specification: the image specification, so a standard for the container image, and the standard for the runtime. So basically, everybody that wants to build a runtime can do that, but if they comply with OCI, then they can run all the containers that you build, for example, with Docker, and run them with another runtime. And if you build them with another tool, you can run them with the other runtime. So therefore, that's the initiative that is important to know about. Now, when we're looking at the components, we have a container runtime, as I mentioned. And the container runtime is a component that is used for testing, that can manage that container from a runtime perspective. The container run in namespaces, isolated, as we mentioned at the beginning, how you isolate them: C groups, control groups, and namespaces, right? Now, today the most popular runtime is run C, but there are other runtimes available, and in a secure service container, for example, we have run Q as a runtime, and there are other runtimes like kata containers, which are even going a step further in isolation. So therefore, from a container runtime, which is an OCI runtime, so it's OCI compliant, standardized, we need a container engine that is built or has inside the tools for creating a container image, for running the container, for logging, for debugging, for pulling that image from a registry. And therefore, the container engines that exist, you see on the bottom, are as well: Docker, Cryo, Containerd, Podman. So there are multiples. And therefore, this diversification is becoming now more and more challenging in terms of what is best, who is using what. But because of the OCI compliance, it is not that bad to use one tool to build it and another tool to run it. Now, just as an in one foil, a couple of container engines here, containerd, from the cloud native foundation, Cryo from Red Hat, Kata containers that came along from Intel, and Hyper SH, and the Firecracker that was came up in 2018 by Amazon, and the CRI implementation over Scilab Singularity. That's another one for high performance computing use cases. So you see the container engines are diversifying. And with that said, Red Hat decided to go forward without Docker. So therefore, Red Hat and you will see OpenShift will not support Docker anymore. Therefore, the replacement for Docker is Podman as the Docker client clone, Scopio for the registry, and Builda for the build. So therefore, here is simplified said, Docker is replaced with or from Red Hat with Podman, Scopio, and Builda. Okay, all of them build and use OCI compliant container images. So available from Red Hat RHEL 8 and Fedora 29 and OpenShift version 4. That's basically Docker. Now, because of that's Red Hat. So because of that, the question is what we have available today and what is the differentiation between them. So Docker basically has one disadvantage, basically, that you have a daemon that has to run all the time, and it's a single daemon, single point of failure. Podman, those containers which are using Podman do not need a daemon. So Podman is running without a daemon. It's a function as a service. So basically, if you want to instantiate, it's starting a function and stopping it when it's finished. Therefore, that's number one. Number two is Docker needs root privileges. All Docker operations have to be conducted by a user with root authority, and typically you automatically get root access. Well, with Podman you can run rootless containers. Okay, so that you can start containers as a normal user. You do not need to have root access. Networking is a little simpler, or the CNI, which is the implementation, or the OCI implementation as well, and therefore it is how we can compare Docker and Podman. And one more thing is, if you have Docker tools, the alias Docker equal Podman can replace the Docker command line name, and you can use your commands as you have them today. So basically the command is the same, just if you use Podman instead of Docker, it is using another module for the container work. Okay, and you have a couple of details here. I'm not reading at all, and the link for that, Podman and Builda for Docker users. If you started with Docker, if you did not start with Docker, think of how you would start depending on which distribution you have. And therefore, from a distribution perspective, what we have available today on Z and LinuxONE is Docker and Podman. So basically what you see is that Red Hat discontinued Docker with version 8, so starting with RHEL 8. And SUSE has them both still. It's Docker and Podman that is available on SUSE and on /15 SP1 and SP2. And Ubuntu, I see I did not enter Ubuntu here. With the 2004 is available. We have Docker there as well in Ubuntu. So we'll see, we see that different distribution partners are going different paths, and Podman is making its way into the distributions one by one. Now, as a container orchestration, I have a couple minutes left, hopefully. I see that the time is advanced. Container orchestration is done by Kubernetes and Docker Swarm. Docker Swarm got discontinued more and more, and therefore Kubernetes is the tool for container orchestration. And Kubernetes itself, also seen as K8S, and if you don't know what K8S means, it's the number of letters between K and S and in the word Kubernetes. K8 letters and S. Okay. Kubernetes defines itself as a cluster. So you see that you have master nodes that are working then with worker nodes, and the worker nodes are not working with single containers. They are working with groups of containers. They are called pods. So therefore, a pod is a group of container, which we can also call namespace if you want, the pod. But based on those pods, the control of is used in the worker node. So basically, when we're looking at workloads in a Kubernetes, we're looking at the workload in the pod versus in a single container with Docker. Okay. Kubernetes is not running the containers, it orchestrates them. That's very important. Now, when you're looking at Kubernetes, that's on top of the container engine and the container runtime. So basically, it is using something called kubelet as a node agent for the worker nodes, and the worker nodes is then working with the container engine and runtime. With that said, Kubernetes says, it's fine with me. If you have an OCI compliant container engine on container runtime, I can do everything you want, because Kubernetes says what's below me, I don't care, as long as it is OCI compliant. Therefore, you see here that the different runtimes are all working with a kubelet. So on top, you see the kubelet overall. So that's Kubernetes interface. And then underneath it, you have the Dockerd, Containerd, runC, Kata, Firecracker, and Singularity. Basically, those runtimes and container engines that Kubernetes can use because of the OCI compliance. Now, looking at Kubernetes from the Docker and non-Docker perspective, you see on the left side the Docker tool set, and on the right side the tool set that is coming with Red Hat and OpenShift, basically Scopio, Builda, Podman, and Cryo, and therefore it is the possibility to use all of them with Kubernetes. So therefore, if you know Kubernetes, you can use all of them. And the offerings that you see that are around, like OpenShift, Cloud Foundry, or IBM Cloud Private, these offerings have tool sets now on top of the Kubernetes core functions that are enhancing that functionality. So basically, the differentiator is the tool set. And therefore, OpenShift comes with a different tool set for infrastructure, development, application catalog, and so on. And Cloud Foundry is doing it similar but a little different and with another tool set and so on. So therefore, you see the offerings differentiate there, but the commonality is that at the heart of their orchestration is Kubernetes with a container engine, a container runtime, and the pods where your container and application run. And because of OpenShift now, we announced OpenShift, or we made it available in version 4.2 in February, and in April 4.3 came available, and that is an ongoing process. So therefore, OpenShift on Z and LinuxONE is the tool set for building, orchestrating, and deploying, or controlling container landscapes on Z. The entire environment runs on Z. So therefore, with OpenShift version 4 versus OpenShift 3, Red Hat put together OpenShift tool sets and the operating system itself, and that's why they replaced RHEL with Red Hat CoreOS, which is a thin containerized operating system, and therefore the entire OpenShift environment is a containerized environment. And therefore you can deploy it, and you have on top of that environment, you have these automated operations with cluster services, application services, developer services, and that's the value of it, having all put together as an enterprise Kubernetes environment, and that's called OpenShift version 4. OpenShift is, as I mentioned, a layered system with these different services. I'm jumping over this chart because we're getting to the point to ask ourselves how to install, how to build a such environment, and you have two options. One is the installer provisioned infrastructure that you can build that and even deploy the infrastructure for that OpenShift environment, and the user provisioned infrastructure, where the user is responsible for building the infrastructure or deploying that, and then the OpenShift environment on top of it is built or is installed in an automatic form. And guess what? We started with UPI. So that's why the environment that is running on Linux on Z or on IBM Z or LinuxONE is basically a UPI environment where you need a ZVM LPAR, ZVM 7.1, and then you deploy 3 master nodes and 2 worker nodes as a minimum deployment, and then you connect that to your load balancer and the services, external services, and have an OpenShift environment in your Z running master and workers completely on Z. As I mentioned, it's based on CoreOS, not on RHEL. You don't see RHEL anywhere. It is CoreOS, and it is built in a ZVM, one or multiple LPARs of ZVM. You can have multiple LPARs for high availability. Okay. Now, IBM's response to OpenShift is to build the software now based on the concept of OpenShift with these common operational services, and build the software in containers, package that together, and sell it as so-called cloud packs. So the cloud pack is a combination of OpenShift, common operational services, and the certified containers. So OpenShift is part of the cloud pack. Okay. And there are 6 cloud packs which are now in development. One of them is available. Cloud pack for applications is available on Z now, and one by one we will see them coming up. And there are different areas where they're focused on data, on integration, on automation, multi-cloud management, and therefore it is an area of growth, and is an area where container workloads will become more and more popular in our data centers. And with that, one thing that is available today as well is the ZOS broker, cloud broker, the ZOS cloud broker, which is able through OpenShift to manage ZOS. So basically you can use the ZOS cloud broker to do the management. Since fourth quarter 2019, that is available, and therefore for ZOS today you can use that. As a summary, why containers work? Well, because the developers can worry about the inside, and the operational guy can worry about the outside of the containers, and configure them once, run anything, and the developer can build them once and run them anywhere. Basically, if you have that deployment pipeline, as I mentioned, you can use the multi-architecture deployment and development to do that. And therefore, I think container will be the technology that will make it easier to have multi-architecture applications. And with OpenShift, we can manage those applications and the environments, lifecycle, and so on. And as last, here you have open source containerized software for Linux on IBM Z. And you see the column that is used, that is mentioning containers that are available. And then also, if you want to look at the public Docker Hub, containerized software, and you click on the IBM Z tag, you will get all the containers which are developed for multiple architectures, including IBM Z, and there are lots of them. And therefore, you can use them in zCX, and you can use them in Linux on Z, no matter where you want. Here you can download OpenShift for IBM Z. You will see here IBM Z and LinuxONE can be downloaded and tried, and also in their cloud you can exercise with it. And with that, I'm sorry we're a little bit over time, but I hope you got some useful information. And if there are some questions, I'm still here to answer. And if not, please send me an email and we can discuss offline or more in detail about containers, OpenShift, and your projects.
Thank you very much, Wilhelm.